In the last video, we found the posterior PDF for the mean and the standard deviation of the noise in a system of measurements drawn from a normal population with an unknown mean mu and variance sigma squared. Then we showed that the marginal probability for mu after integrating out sigma was the following. And we never showed what the marginal probability distribution was if we integrate out mu instead of sigma. So let's do that integral right now. Alright, so here actually I made a mistake here. I wrote down this marginal posterior PDF assuming we had a Jeffreys prior. So if we had a flat prior, then I should have put a plus 1/2 here, and that would be consistent with this in this expression. Or I can decrease this and this one to be consistent with the prior probability. So this is assuming is proportional to 1 over sigma. And here in this integral where I marginalize out mu, I pulled out all the terms in the joint PDF that don't depend on mu explicitly. Now if I look at this integral here, this is a Gaussian integral, and we know that the normalization for the Gaussian is 1 over sigma. That means that this integral must be proportional to sigma. And since I only know the integral up to a proportionality constant, I don't need to know anything more about this integral other than it evaluates to a term proportional to sigma. So therefore the marginal becomes and now I'm going to show how we would implement this marginal PDF and this one in MATLAB. So I'm going to write a function that takes in two inputs, one a list of mu values, oh this is not what I meant, and the data set, and evaluates the log of the posterior probability at the mu values. And so we want to implement this expression. So the first thing is we need to know what mu hat is. So that's simple. Mu hat is equal to the sum of t divided by the length of the data set n, and so n is the length of the data set. And then I can evaluate the expression over here. And then I need to normalize. All right, let's go through the code. So first we bring in a set of mu values. We extract the length of the data set, compute mu hat, evaluate the residuals, which is the data minus the model, calculate the log of the posterior probability. This is, there's an arbitrary constant missing here that I don't have, which I'm going to need to evaluate through the normalization. I take the log of the posterior, the marginal posterior, and this is vectorized here, so we'll evaluate for each and every value of mu. Then I subtract the maximum log probability from the log probability to avoid underflows or overflows, and then I normalize by first integrating out the PDF and dividing. Now here there's the assumption that the range of mu I pass into the function are large enough to get all the significant amount of probability. So the tails might be pretty wide if I have a small data set, and I have to make sure I put the range big enough so that this will be properly normalized and I don't truncate at the tails. But let's evaluate it. So first thing I'll do is I'll create a data set. So let's say we have 100 data points, and let's suppose that the standard deviation is 2, and that the mean is 4, for example. So here I should put mu. So I should get data that are normally distributed about a mean of mu, and a variance of 16 sigma, no, a variance of 4 sigma squared. And now I'm going to make an range of mu values to pass into these functions. So mu range in space. So I have 1,000 points. I don't know if minus 8 to 8 is big enough. Let's put 12 to be safe. Okay, so I create a range of mu values, and now I'm going to evaluate the probability function. So P is equal to prob, oh, it's called EG1. I need to change that. And then I will plot it. All right, let's see if I've coded it right. EG1. All right, so that looks pretty nice. So the posterior appears to be peaked around the value of 4 very closely, and the error is pretty small. That's because n is quite big, it's 100. Let's try it again for a smaller value. Suppose I have only 8 points. It's still fairly well centered, close to 4. Now the error is much wider. So how can we check whether the answer is right or not? I'll leave that as an exercise. Let's implement the posterior probability for sigma. So I go from 0. I know that the, oh no, I'm using a Jeffreys prior, so I should pick my range to be from minus infinity to infinity, and then in log space, and then convert back to sigma space. So I'll do that. All right, so I picked a range between minus 8 to 8 for the logarithm of sigma. Then I re-exponentiate it to get the correct range. And now I can compute the posterior probability. So this should be probability of mu here, now that I changed the names. All right, so for figure 1, we're going to plot the mu posterior PDF, and for figure 2, we're going to plot the sigma posterior probability PDF. Oh, I forgot a comma. Set, I see here, this would be sig range. Okay, so this is the posterior PDF for sigma, and this is for mu. So all the probability is stuck around here, and I have this very long tail. So what I'm going to do is 2 things. First, plot the posterior on a semi-log x-axis. All right, that's a little bit better. And then maybe my range might be a little bit too broad. So maybe I don't need to go all the way to -8. Okay, so where's this one peaked? Let's check if it's close to the true value. So somewhere between 2.05 and 2.1, and the value that I picked was 2. So it seems reasonable. I don't know if it's right. Let's pick more data points. They should get, oh no, let's put a lot of data points. Then they should get very narrow. Right, then they're super narrow, and then I could try to refine my mesh to be more points concentrated close to where the posterior probability is located. Let's go back to a small sample size. And let's change the values of the parameters, see if they change correctly. So I'm going to change mu to -4, and I'm going to change this to 20. All right, so this seems to be in a close range to 20. Let's look. It's quite a bit off, but it is a small sample. Also, the peak, the most probable value, you notice how the distribution is quite skewed. So what I should do is compute the expected value and compare that. And this one, my range just simply isn't big enough. The posterior PDF is so wide, and I can't really see what's going on. So I would have to make my mu range wider. Okay, so that's a little bit better. Let's see if it, and now I'm going to add code to compute the mean or the expected value of sigma and mu from the posterior. So let's do that. So I'm going to integrate p multiplied by the mu. And this is known as the expected value. And I'll do the same thing down here for sigma. And then I'll write them to the screen. Alright, so the posterior estimates was -8 and 16. For mu, I had -4. And for sigma, I got 16 instead of 20. Now, it's hard to know if these are good estimates or not because I have a small sample and I have pretty big error bars, so I should try to compute the error bars of these quantities. And for mu, I noticed that I truncated my tail before the probability dropped enough, so I need to extend the range out further in the negative mu direction. That's one thing. The other one is I need to have a way of summarizing this probability distribution because it's kind of not that symmetric. So if I take the expected value, the error bar is not going to be symmetric. But it could serve as a rough estimate. So let me first increase this range to maybe -40. 40. Try it again. Alright, so now this one looks a little bit better, the PDF. And for this particular sample, I overestimated sigma, 22 instead of 20, and -4 this one time. It turned out pretty good. So perhaps a lot of the bias last time was because my tail didn't extend far out. In fact, it doesn't quite go far enough still, so I'll go all the way to -50. And let's try again. Clear all. Okay, so it seems to be producing reasonable results. Of course, there's still some more tests would need to be done to properly test the code. One thing for summarizing the width of the PDF, one thing we could do is find out, integrate how much of what are the limits to capture, let's say 95% of the probability under the curve in either case. So that by finding the upper and lower bound that captures 95% of the probability, we can ensure that we can deal with probability distributions that are not necessarily symmetric. I'm going to leave that as a homework, And here I'm just going to do, I'm just taking the standard deviation of these distributions. So let's do that. So here I just take the expected value of mu range minus mu hat squared. And then I take the square root to get what's called the standard error, which is the standard deviation of the posterior PDF for mu, as opposed to, so it's like sigma, but it's the sigma for the probability of mu, not for the probability of the data points. So there are different standard deviations and it can be confusing. So here it's the standard deviation of the posterior probability for the standard deviation. And again, I remind you that these are not very good error estimates because the PDF is not symmetric. In the limit where I have large data set, it's going to become better and better summary of the uncertainty. All right, so I got mu, I got 5 plus or minus 11, and the true value was minus 4, so that's pretty good. It's actually, the error bar seems much wider in this case, but it's fine. For sigma, I got 34 plus or minus 9, so the true value is at 20, is outside this error range, but of course this is just one standard deviation, so it has a good probability of being outside the range. Let's try again. So this time it does include, the sigma does fall within the confidence interval, and it does also for mu. All right, this is where I'll stop.